Welcome back. What we're going to look at today is, do heavier people swing faster than light people on children's swings? You might also have noticed the new titles to FJ's Physics, and my thanks go to one of my pupils, Bertie, who made those wonderful aluminium castings in the Design and Technology department. Absolutely fantastic, and we're going to use that now as the title for FJ's Physics. So, young Barry's reached the age where he enjoys getting on children's swings and swinging up and down, and we've got one attached to the door frame in the house which he plays with, and I'm certainly not going to try and get on that. I'll almost certainly break it or pull it off the roof. But we nipped out to the playground the other day, and there were two swings side by side, and I kind of crammed myself into one of them and he got into the other one, and we both started swinging. And what I wanted to look at was, I'm clearly a lot heavier than Barry, so will I fall faster? Will I swing faster than he does and do more swings up and down than he does in a minute? Or will he, because he's lighter, kind of move better, feel less air resistance and things, so will he swing more, in other words, with a higher frequency? The result, I think, will surprise you. So, you've seen the little bit of video there, and I hope you noticed that within variations, small variations, the strange thing is that Barry and I swing at the same frequency. I mean, theoretically, we could hold hands and we go up and down together. Now, I'm many times heavier than him, so that seems quite strange. So what I'm going to do is I'm going to show you what's going on this little laboratory swing that I've made earlier. So, to simulate what was going on there, I've made myself a little children's swing. And here's Barry, the small Playmobil person, and I've made sure that they're a very low weight. They have a low mass. Not many atoms there, if you see what I mean. And here I am, or Bob the Builder, on his lunch break in the park, playing on the swings. And I've put a lot of weights here. In other words, a lot more mass, a lot more atoms. So, what I'm going to do is pull the heavy and the light one back and let go, and let's see what happens. Okay, so here goes. Let's pull them back, and 3, 2, 1, go. And I pulled them back the same distance, though that doesn't actually matter too much. And you'll notice, basically, they swing together. Okay, let's try that again. 3, 2, 1, go. 1, 2, 3, 4, 5. They're pretty much swinging at the same frequency. Now, it might not quite be the same, but the point is that with a bit of string and a very low mass and a much, much larger mass, 1, 2, 3, it's pretty much the same. So, what's going on here, and how does each swing know to swing with the same frequency? Now, just before we answer that, some of you might say, well, what happens if you pull them back a different distance? You have a different amplitude. Well, that isn't really what this video is about, but let's do it anyway. I'll just pick Barry, for example. 1, 2, 3, 4. That doesn't make any difference either. So what I'm going to do now is film it from the side so you can see the two of us moving together at the same frequency and in phase. Okay, so here's a side view like the one we took of Barry in the park, and you'll see that basically the very light person and the heavy person swing together. And if you release them at the same time from the same height, the same amplitude, they're in phase. They move together. They could hold hands and they oscillate with the same frequency. It's independent of their mass or weight. The mass or weight makes no difference at all to the frequency they oscillate at. So we've got some explaining to do. So I'd like to put this video in the bracket of counterintuitive physics. It depends on how you think about it. You could think about it as the heavy one gets pulled down more, so that one is going to reach the bottom quicker. Okay? Or you could think about it as the light one finds it easy to get going, doesn't need much force to make it go, so the light one will get down to the midpoint first. It'll move faster. But in fact, they both move at the same rate. It's actually a changing speed because they're slow, fast, 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 slower, 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 and then faster again and then slower. But the frequency of the oscillation is the same. So now we've observed it really well, let's see what we can do to explain what's happening here. So the physics of this is actually quite easy, really. You can get mathematical about it and look at F equals ma, force equals mass times acceleration. Okay, but I'm going to look at it in a slightly more wordy way. Let's leave the maths for a minute. Okay, this one is much heavier. It's got more mass, and if I punch it, it hurts. It's quite hard to get going. Whereas if I punch that one, it gets going easily. Okay, so that's the first thing to understand, that large masses don't like speeding up. So this one is going to be left behind, isn't it? Because this one likes speeding up. But remember what gravity does. Gravity pulls on mass, and it pulls more on a heavier mass than a lighter one. So what does that all mean? The heavy one doesn't like to get going. It's got inertia, but gravity pulls it more and says, come on, get going. And the light one, okay, does like to get going, but gravity pulls on it less because it feels lighter. And so it doesn't rush ahead. So you need to sort of think about what I've just said there, but think of the high mass not wanting to get going, so gravity puts a large force on it. And the low mass wants to get going, but gravity puts a weak force on it. And those two things cancel out, as it were, kind of average out. Bad use of scientific language there, but I think you see where I'm coming from. So the acceleration of the two is identical. Okay, it doesn't make any difference. These are falling masses, and you might have seen one of my videos on dropping different masses in my laboratory, and it doesn't make any difference if it's a large mass or a small mass. Gravity is so clever. It compensates by pulling harder on larger masses to make them move. Okay, let's break with tradition just for a short period of time before the end of the video. So F equals ma, force equals mass times acceleration. And acceleration, is force over mass. So this has a bigger force divided by a bigger mass. This has a smaller force divided by a smaller mass. So those two numbers come out the same. Okay, in other words, the ratio of force to mass is identical, so these two have to fall at the same rate. And interestingly enough, I don't know if you can see it, there's a fly up here, or a fly going through the video, so that's learning some physics as well. Brilliant, so I hope you enjoyed that video and learnt a little bit why, when I'm on the swing and Barry's on the swing, even though we are different masses, we will oscillate with the same frequency. And the final little twist here is, how could one of us oscillate with a higher frequency? Well, that depends upon the length of the pendulum. And the length of the pendulum is from its fixing point to the centre of mass, which is just above the middle of these masses. So these two pendula, are the same length. And if we change the length, everything would change. Length affects the frequency, but not mass. And maybe that's a topic for another video.